Hi everyone, today we are happy to have Fangchen here to present her great work. Fangchen is a research scientist at Google DeepMind. Before that, she obtained her PhD from UC Berkeley, advised by Professor Peter Beal. Her current research focuses on developing scalable solutions for generalizable robotic manipulation, including word models, vision language action models, and cross-embodiment learning. In the past, she also spent time at Google Research Fair and media research, where she worked on reinforcement learning algorithms. Now I'll pass the floor to Fangchen. Welcome.
Thank you, Roger, for the introduction. And I'll start my presentation with the title of Generalizable and Scalable Robot Learning in the Physical World. Yeah, so the intro slides may be pretty similar with everyone else in the world. We all know that language and vision foundation models have achieved great success by training on internet scale data on vision language tokens, which gave us like very reliable chatbot coding agents or visual generation tools that we are using every day. However, as a person who are working on robotics, we may hope that we are also able to achieve similar robot foundation models that gives us a general purpose robot, helps us in the daily life. For example, as shown in these videos, it's able to cook for human, deliver packages for human, and also like help with human in the daily life. But however, yeah, at the same time, I think last year, also beginning of this year, we have seen a lot of fancy demos from everywhere in the world, like from every startups, big companies, or like Chinese Spring Festival gala, like cool robot demos are everywhere. However, I'm pretty sure when you are trying to submit a paper or record a demo for some conference, that's maybe something you will more commonly see a lot of execution failures when you are trying to deploy your models. So this video is from Mobile Aloha. So here is like a very famous paradox from Moravec, like why robot foundation model is so hard to achieve and so unreliable. It requires a lot of cherry picking to have a fancy demo. So basically, he's saying like, what's easy for human may be very hard for computers. Like for this type of very basic sensory motor skills, that's trivial for a kid. It actually takes millions of years of evolution to achieve there. However, for like some video games, some chess games go, this type of like task may be easier for computer to solve, but for sensory motor skills, it's actually a more complex problem. It takes the evolution of maybe embodiment systems. It's not only a data or algorithm problem. If we take a look at the difference between physical AI and digital AI, we know that digital AI, it already has trillions of tokens in the internet, and it also has very compact representations like this image text tokens maybe easier to align with each other, easier to be tokenized very well. And also we just like kind of call these agents, let it generate visual contents. If it generates something that is not desired, we just ask it to generate again. So it's different from robotics. So the reset there is very, very easy. But for robotics, it lacks in domain high quality data. At the same time, the control signals is very complex. It's very high dimensional continuous and don't have maybe semantic level information. Also, we have to deploy the robots in the real world to take physical interaction. Sometimes it messed up a scene or destroy some objects. This is something we are unable to recover, unlike digital agents. So that's all the challenges robotics have, and there are some data that we can leverage for robotics. This is pretty similar to Yuka's data pyramid, which he proposed a few years ago. So basically, the smallest yellow dot is the teleoperated demonstrations, which are in the smallest scales. But it's actually very trivial, very easier to give us some specific behaviors. We just run behavior cloning on top of it. But like this type of data is harder to scale up. At the same time, we have the larger pink dot, where I call it diverse sensorimotor data, which can be simulated data or some real-world random play or real-world failure trajectories. This data cannot directly give us specific expert level behavior. Like we cannot run behavior cloning on top of it. But however, it still reveals a lot of information about, for example, the dynamics of the embodiments or the MDP distribution of the task. So we can still like do a lot of things using this type of data. For example, we can do modeling and planning to obtain diverse basic scale, where I call it low-level generalization or scale-level generalization. And the largest circle is internet scale data, which are used to train language models and VLMs, and already been proved pretty successful in open-ended perception task reasoning. This will give us high-level generalization or task-level generalization of the behavior models we want. So that's the overview of the three types of data, and I will also talk about my past work in this three aspects. I will first talk about some early work in my PhD that's focused on maybe low-level generalization, and then maybe later on I'll talk about some. Oh, sorry, the internet here may be a little bit slow. Never mind. So I'll talk about some later VLA work I did in my PhD, and then I'll also briefly talk about some efforts I worked on for this portable device to scale up the real-world demonstration level data. Okay, the first work here is mass autoencoding for scalable and generalizable decision making, which is a paper accepted by NeurIPS 2022. Before that, I was working on some RL algorithms. So this paper is actually very RL motivated. So back to this, people are designing a lot of exploration algorithms. For example, this curiosity-driven exploration by having the discrepancy of prediction and real states, or this skill-based skill discovery-based type of intrinsic reward, or this type of particle-based uncertainty quantification type of reward. But like all of the algorithm just focus on maybe help the agents to explore better with the MDP, but they are not thinking about how to leverage the data that stored during exploration. So here is a work that first studies how to leverage exploratory data. Basically, it stores all the exploration data during the exploration stage, and then it relabels the every transition with maybe task-specific reward rather than the original intrinsic reward. And it found out that performing naive or policy RL on this very broad exploratory data can give you SOTA performance on all the offline RL benchmark. So basically, you don't have to do many fancy offline RL constraints, different terms or whatever. Just run off policy RL naively on a diverse data set. It's already able to give you the expert level behavior. Also, feel free to ask any questions during my presentation, if there is. But however, this work also relies on, we have the ground truth reward for the task, for different tasks. So can we maybe relax this assumption? For example, can we obtain diverse behaviors without relying on the reward? And the answer is yes, we can obtain diverse behaviors through word modeling. So that's the contribution of this paper. It's the first approach to blend inverse and forward dynamics model in an all-in-one transformer through mass autoencoding. So it's like a framework that unifies decision prediction and word modeling. So why I'm saying this is like, maybe I will first take an overview of this approach. So basically, there are some input trajectories, which is a sequence of state actions. We randomly mask some state and actions and use a bidirectional transformer to decode the original sequence of the trajectory. And if we take a closer look at how it is trained, For example, if we mask this states here, then this model is doing the forward dynamics. And if we mask the actions but unmask the states, then this model is doing inverse dynamics prediction. So by doing this randomly masked trajectory autoencoding, this model is actually learning both the forward and inverse dynamics on this specific task. And actually, we can, after training this model, which is just like a very unified, using a very unified training objective on diverse data, on diverse exploratory data, we can actually use this model to perform different downstream tasks by just having different mask patterns. For example, if we want the agent to reach a goal, maybe t step away from current state, we just mask all the intermediate tokens and have a goal, maybe t step away. Then this model will decode the actions to achieve this goal. This is more like long horizon inverse dynamics. You just mask all the intermediate steps, and this model is able to reconstruct a plan for you. And also it can perform long horizon so-called forward prediction or scale synthesis. Basically, we can prompt this model with maybe an ant running in certain speed, have a few trajectories here and mask all the future tokens. Then the model is able to predict actions for the ant to maintain the speed. Or like it is able to do maybe certain speed running or backflipping based on the skills you are prompting it. It's able to generate the future. And also it's able to perform both single goal reaching and multi-goal reaching. If you have multiple sub-goals, you just also just give it a certain time steps. This is kind of like optimization-free collocation. It's able to sequentially reach these sub-goals based on the reconstructed plan. Yeah, here is some dataset overview. We have this quadruped worker cheetah domain, and we have trained policies follow intrinsic reward or mixture of intrinsic and extrinsic reward, and also train some near expert policy with extrinsic reward and store its past replay buffer. So actually, this is a pretty diverse data set, contains very diverse motions. Some of them are near expert, but majority of them are some random exploratory trajectories. And that's the data set we are using for training these mass trajectory models. So here are some results. Here are some goal reaching results. It's showing the distance to the goal for maybe single goal reaching, multiple goal reaching. The lower the better. We can see that this type of bidirectional model is better than like some autoregressive model, which I call Go GPT here. It should be something like decision transformer, which is predicting the future action autoregressively. Like this type of bidirectional models has awareness of the future. It's better at giving you reliable action plans to achieve like a sequence of goals. And also it's able to predict future action patterns based on the few prompts we give. Here are some comparisons with MassDP and GPT, like autoregressive models with ground truth oracle, which is like the expert behavior. So there are some reward it's supposed to get. The higher, the better. We can see at MassDP with closed loop is comparable with the decision transformer fashion autoregressive models, and also matches with Oracle. Also, we can perform offline RL fine-tuning on top of the model we trained because it's learning some maybe useful representations using forward and inverse model prediction. So maybe it's able to discover the most important actionable representation in the states. So we also kind of fine-tune actor and critique on top of the representations given by the model. And this is kind of, so this model actually performs similar with like also autoregressive models. Here the summary is like, it's the first work to unify the word model and decision prediction in a single framework. And it used very simple general pre-training objective, which is just reconstruct the mass trajectories. from like diverse exploratory data. And it's able to generalize different downstream tasks, like all these goals and prompts, they are out of distribution, like they are not in the training data, and also can be efficiently fine-tuned to perform offline RL. For like autoregressive generation tasks, it matches with autoregressive model. For goal-reaching tasks, it's significantly better than autoregressive model. So the limitation is like it's only for locomotion tasks, only in simulation, and it's mainly good at like a significant good at doing this goal condition tasks. For generations type of stuff, it's kind of matches with autoregressive model, so it's like no significant advantage. But the main limitation is like still it's in simulation, it's for locomotion. So the next thing we're thinking about, maybe can we maybe train a robot manipulation policies, but with more diverse and general task specifications. Just let me know if there are any questions during this presentation. So yeah, I'll talk about some of my VLA work in the later stage of my PhD, which leverages internet scale data to achieve task level generalization. The first work is MoCA, which is a paper accepted by RSS 2024. So here we are thinking about tackling the term called open world robotics manipulation. So what is open world manipulation? Basically, it means that we don't have any assumptions on the language instruction on the objects or on the scene. So basically, there's no predefined distribution of the task, but you can assume the task is from some natural distribution or in the wild distribution. So for certain for this type of settings, you have to use a VLM or some sort of pre-trained model because you don't have any assumptions on this like task specifications. So you have to use pre-trained models to get this type of prior. But however, like VLMs back to then, maybe nowadays they are better, but it's not good at a lot like low level understandings. Maybe, for example, there is a picture of a lot of people in the scene. It's only able to give you like what's roughly happening. But maybe if you ask how many people in the scene, it's not able to give you the correct number. So because of this, maybe it actually lacks understanding of the environment and robot control, like motion understanding. So maybe it's very hard for it to be directly used by us. However, there's a work called Saddle-Mark visual prompting. It's also like 2 years ago. Basically, it says GPT-4 naively is not good at visual reasoning, but however, they just did a pretty naive thing. They just segment all the objects in the scene and mark it with numbers, and they found GPT-4's visual reasoning capability got significantly boosted. It's able to perform spatial reasoning and also counting this type of visual reasoning tasks by having this object marked. So motivated by this, we're thinking about maybe we should mark something for robot motions. So what's the best representation to mark on the image? So the answer we had back to then is K points. So basically, for example, almost every task, every not like a quasi-static manipulation task, you can kind of define that using a set of K points. For example, this is like a sweeping this trash off the table. We have a grasp point. We also have a function point, which means that this should interact with the target objects. Like there's a target point on the object, means these 2 points need to be interacted. And also if you want to define the motion, we just need a bunch of waypoints. Here we just use 2, like a pre-contact motion and post-contact motion waypoints. So basically you just kind of decompose the task with a set of K points, and almost every task we have in the mind can be actually decomposed like this. So the good thing is like all the prediction can happen on the 2D images, and it actually can specify diverged range of motions. And this is actually agnostic to embodiments. You just hard code a bunch of primitives to reach or grasp the point you specified, and you can just deploy it on the robot. Okay, yeah, so I'll skip the details for how the prompts are designed, basically a lot of natural language and examples and explanations. But high level is basically like we first decompose the task into maybe k stage, and for each stage, we segment the corresponding objects and get the segmentation mask, mark all the points on the boundary and on the center, and then kind of divide the image into 25 tiles, and then ask GPT-4 okay, which point are the grasp point, which point are the function point, and tell me where the waypoint should belongs to, like which belongs to which tile, so something like that. And then GPT-4 is able to generate, like answer you, like maybe P2 is a grasp point, and sorry. Oh, P4 is a function point, blah, 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 whatever. So we got the answer from GPT and then hard code a bunch of primitives to grasp, reach, and sweep. So here are some videos of the tasks we are able to perform. So here's the query image, and here's the generation from GPT. Yeah, basically it's able to match the performance of code as policy and works poser. But we like works poser is not able to handle tool using tasks because it's not modeling the work source for the tool or something. So some details there, but basically it works as well as language model. That's the takeaway. And it's also robust to instructions and objects. So basically the takeaway of this work is we now have a system that can perform training-free open world affordance reasoning and planning, but the system fails due to various reasons. So sometimes we have wrong perception. Some objects involved are not recognized by grounding nano. Or sometimes GPT-4 gives us a very like a not like a wrong decision on which key points to interact. And sometimes our low-level primitive got failed because of maybe some wrong sensors, depth sensors not accurate. So basically, it fails due for different tasks. It can fail due to different reasons, and you have to tune all the modules, figure out why it fails for every task. So it's pretty annoying. So after this work, I'm thinking about maybe we should design some generalizable policy, which is maybe VLA policy that is pure data driven and data efficient. So every time it fails on a task, we just add a bunch of data and fine tune it, and then it works well. Maybe that's the way to go.
Hi, Fangchen, can I ask a question?
Okay, sounds good.
For the waypoint, I'm wondering if you ask GPT-4V to label on 2D, then how do you know the height? So if we want to wipe something on the table, and is the waypoint always on the table, or
that's a very great question. We just hard code the height. That's true. Yeah, it's like we hard code maybe different like quantized height, like something on the table or something we feel is on the air. Like if we want to drop something, like the waypoint is actually on the air. So it's some sort of hard coded stuff.
Okay, thank you.
Because like it's only able to give you something on 2D images. So for waypoints, it's on the free space. So it has ambiguity in 3D. So that's why we have to like hard code heights for different tasks. If it's tabletop task, we just hard code the tabletop heights. But for all the other points on the objects, because we have the object depth, so it's something we can read on the objects. But just like the waypoint, it needs a specified height. Yeah. That's a very good question. Okay, let's continue. So to obtain such type of VLA policies that's generalizable, maybe we can take a look of all the past VLAs back to then. This work was published as like RT's OpenVLA octos. Later on, they got Pi. but all of them are used pre-trained vision encoders, vision language models, because the pre-trained model can give you some robust representation because it can see more data. And sometimes if you perturb the scene, like different lighting conditions, slightly different tabletop, this type of model are still able to encode the scene with robust representations and helps you still maintain your pre-trained behavior, still maintain your behavior robust to this type of condition changes. At the same time, there are a lot of work focused on what type of visual representation we should use. For example, MAE type of visual representation, or this time contrastive R3M type of representation, or a mixture of MAE and R3M. So basically, this work are just naively bring what happens in the vision self-supervised learning field to robotics. But there are some limitations. So each work has its own conclusion. It got inconsistent performance across tasks. Sometimes MAE is better, sometimes R3M is better. It's very hard to say which representations are good. And all the learned representation are just some general visual features. They are not actionable or task aware. So here is this work. So VLM needs task aware visual features. This is accepted by SAML 2025. Yeah, as I introduced before, like naively using all the visual representations, maybe it's helpful, but just helps a little bit. But how to make the best use of the visual features. So also motivated by this work called Clear Clip. Basically, we all know that CLIP is trained on millions of image text pairs. It should have very good understanding of image text alignment. But however, CLIP is actually very semantic or very high level. It just gives you roughly understanding of a whole image. But however, this work is pretty interesting. It says actually CLIP has very low level or fine-grained understanding of text image alignment. It can do text patch alignment, but just don't use the final output of CLIP, but use intermediate representation from CLIP. So basically this X out is final output of CLIP, but X attention is something before the feed forward. So this feature gives you somehow gives you very clear correspondence between text and patches. For example, there's an image. I query the image with sky, ground, and person. For the final output or the residual, it actually gives pretty noisy correspondence. But for this, somehow magically, for this X attention feature, it's able to segment the sky, ground, and person very well. So it gives you text and patch correspondence nicely. So after reading this paper, we tried this on our robotics dataset and also OpenX embodiment dataset. So we take a clip and we compare its final output, the text patch correspondence, with the intermediate X attention feature, text patch correspondence. We found that actually it works surprisingly well on our robotics data too. For example, blue cube is able to highlight the corresponding objects. And also red ball, green triangle, like it's able to just give you the patch that corresponds most to the text input. And it also works for OXE, like Coke. Vegetable is hard to see here. Oh, there's a carrot. You can see it gives high correspondence here. So basically, it really seems like this clip model, this intermediate representation of clip model can gives you very like low level fine-grained text patch correspondence. So motivated by this, we were designing some strange architecture here. So for example, this is a standard clip text encoder and vision encoder. We got text embedding from each text token and patch embedding from each patch token. We calculate the similarity in this based on this X attention And so basically visualize here is flattened here. It gives us a heat patch corresponds most to this text token. And then we do an average sum using the heat map and the patch tokens. So this gives us a test pooled visual tokens. This is kind of complicated, but you can imagine this as it's not the average pooling or max pooling. It's basically you're pooling the visual tokens based on the text similarity. Okay, any questions here? Yeah, so basically we are just extracting the weights based on the x attention intermediate representations, and we do a weighted sum based on the similarity. We got this text pool visual tokens. So for after this layer, each text token corresponds to the most relevant. Like it's a soft sum. But it's like a weighted sum of the most relevant patch tokens. So basically, it's like we try to pool the visual tokens using text similarity. So in this way, we are separate the affordance understanding and low-level control. So the clip actually it's a joint tokenizer of text and image, and gives you a feature to like interface the policy, the action generation. So this work this type of joint image text encoder, we call it like joint tokenization. So different from all the other work like Octo OpenVLA, it use separated text and image tokenization. For example, text encoder may be a T5, the image encoder may be a dyno. So this type of separate vision language tokenization requires relearning the vision language alignment in the policy network. For example, your T5 and dyno, they are not trained together. So your policy network have to align the language embeddings from T5 and visual embeddings from dyno, and then perform the low-level control. Use like based on the limited robotics data set you collected. So this makes like the generalization to unseen objects and unseen instructions really hard, because your text and image encoder, they are not trained together during pre-training. But it's like you just take the encodings from them and do some VLA-based post-training on your robotics data, which is a limited data, which is like a limited scale data set. But however, if we use this kind of joint image text encoder, like CLIP, it's already trained on trillions of like image text pairs. It already has vision language alignment, and this gives you the affordance understanding naturally. Then your policy network, something like you post-trained, add an action head or something, this can just focus on low-level control without relearning this alignment. Yeah, so the architecture here is actually very straightforward. We have this vision language fusion layer, which pull the visual tokens based on the text similarity. We also have a text encoder here, because sometimes we ask it to pick up some object, sometimes we ask it to push some object. So we have to encode the primitives specified by the text. Like the vision encoder gives you the objects, like the object affordance corresponds to the instruction, but like the text encoder gives you the primitive type representations. But they are all kind of some MLP projection here, and also this so-called embodiment encoder is basically a proprietary encoder, and we basically concatenate all the features and train a very naive causal transformer policy. The task we have is like we have a pick place data set, like it's basically pick different objects, place it in different containers, and there's some pick up, poke, open close drawer, and pour water from different objects to different containers. Like we have both pick place partition and also full data set, which contains some drawer, pour water, poke, this type of actions. Back to then, there are only Octo, OpenVLA, and Pi0. No Pi 0.5, but we compare ours with all the available VLAs, and find out our model is perform the best both training and unseen tasks. And also this performance can scale up with the size of clip because larger clip gives better vision patch alignment. So we can clearly see the improvements here if we scale up the model. Also, we train our model on more primitives. We can see like pi0 is only good at pick place, but after post-train, after fine-tune more primitives, it's not able to perform all the tasks well. For example, it's not able to identify pouring, and also its pick place performance also dropped. But at the same time, ours scale with policy model size, training data sets, and also consistently outperform pi0. So basically, that's some old VLA paper, but takeaway from this two work is like VLM has the ability to perform open-ended perception, affordance reasoning, task planning, and low-level motion can be classical method or data-driven policies. It can achieve high performance with the correct interface. Last, I'll briefly talk about some portable, the exploration work I did using like a tactile plus portable devices to scale up the teleoperation data sets in the real world. So here I'll talk about like a tactile enriched UMI, which I did in the last year of my PhD. I talk about it because it's this UMI type of portable device solutions recently becomes very popular. So I'll just briefly discuss some future work we can do, and also take a look at the early attempts I did. So basically, when UMI was released, I'm very impressed, and immediately decided to improve on it. So the advantage of UMI is robot-free, more scalable, which we all know about that. And limitation is for the first version of UMI, it relies on the accuracy of RGB SLAM. Actually the RGB SLAM, the open source RGB SLAM solution are not that robust if you really try on it. And also it only records in the effector pose. So of course there will be some IK singularity issue. And also there is no force sensing. So imagine a scene if you are trying to resist a force. So from the observation, your gripper just stops there, but it's actually actively pushing in this direction to resist some external force. So original UMI don't have force sensing and compliant control. That's also a limitation. And it's also just rely on wrist camera, so no scene camera. So it's only able to handle some tabletop, some pretty small scene manipulation. So the work I did is just tackling the force sensing part, basically by just adding a tactile sensing to the finger gripper. This is some existing work, which just kind of put a lot of markers on the finger gripper and adding a camera internally, so you are able to capture the deformation of the gripper. This is just image-based tactile sensor. So this is a kind of scrappy design of the gripper. Later on, we improved that a lot. But basically, we just treat the tactile image and vision together and feed it into policy. It's able to perform more dexterous tasks, for example, interacting with transparent object, which is harder to see in the wrist camera, but you can see that clearly, like the text tube shape pose in the gripper. And also something that is harder to capture by the wrist camera, but easier to capture in the tactile camera. Yeah, so basically there are some representation learning stuff that can make the training more efficient and success rate to be higher. And later on, we also changed this device to be like a VR based, so we don't have to rely on the RGB SLAM. It's actually some some more mature solution that can gives you more accurate tracking of pose. Of course, the cost is higher, but RGB SLAM is really not good if your environment doesn't have a lot of textures. So you have to make your environment more colorful. Like for the white tables, you have to put some stuff on top of it. And also the RGB SLAM cannot handle, for example, this articulated object manipulation. So the thing is changing. So you have to use dynamic SLAM instead. So basically the naive version of RGB SLAM will not work for a lot of cases. Also for bimanual, you're seeing consistently seeing the other gripper moving. So for moving things, this RGB SLAM will also fail to locate where your gripper is. So basically, we'll have to, I think there are better solutions like by integrate a VR tracking device, which use like active red light or something it actually track a changing matrix of red light. So it's no longer using RGB. So basically this type of improvements can make the tracking better. And also if we take a look at Sunday's solution, it's no longer rely on the RGB SLAM. Of course, it has a better tracking system. But however, it still has the IK issues. But if you take a look at their demo, you can see that it actually has a wrist DOF. So it actually helps a lot with singularity. So almost every data the human collected can be kind of solved by IK. So previously, the original UMI, you have to kind of collect in a very awkward way to make sure the IK always have solution. But with the wrist DOF, your IK actually is like almost every data collected using this glove can be solved by IK. And also the IK has like a more smooth solutions. So, like for the original version, without this wrist DOF, sometimes IK is not giving smooth solutions at different poses because IK has more than one solutions. But like the limitation here is still like it's not aware of sync collation. So that's like a fundamental limitation of all the like portable device, like UMI-like methods. So basically, if your scene has more objects, IK cannot give you solutions about how to avoid collision with the scene. So it's only able just to track the where is the end effector, but not really do the collision avoidance. So if your scene is very cluttered, then this UMI type of approach will have a lot of problem. Otherwise, you'll have to design some sort of collision-aware whole body controller to interface with your UMI, which can be a research direction in the future. But like, Sunday here also has force sensing, and it actually not only relies on the wrist camera, it also has an egocentric camera. But that's also kind of open question, like how, because like UMI is like a unified interface, like it's actually a direct mapping from the glove to the robot's end effector. It's the same end effector, so it's consistent all the time. But for egocentric, when people are wearing these devices to collect egocentric data, it's not matched with this robot. Like people have various heights and various like poses, arm lengths, which are different from the robot for sure. There are some ways to calibrate that, but it's also kind of tricky. So maybe just naively scale this up, like collect with a lot of human, different size of human, and make your robot designed to be in distribution of the human, maybe can also work. I'm not sure how, what's the progress of Sunday's design or current solution. Maybe it's like the egocentric one just used for navigation, which I'm not sure. Okay, that's some brief discussion of portable devices. I feel it's pretty popular recently, but there are some takeaways from me. Also, I'll talk about some future works. Maybe we can leverage different source of data to achieve. For example, this diverse sensorimotor data we can maybe leverage large-scale simulation to get robust, dexterous, and whole body controllers. For this internet scale data, we can also leverage human videos, which is a pretty popular trend recently, or motion capture data set or generated videos to co-train with VLAs or just directly combined with robust low-level controllers I mentioned here and follow the reference motion. At the same time, I was also working on like in context models during my PhD. Here are some work I lead or advised, but have no time to present today. Maybe cross-embodiment demonstrations context and sub-goal sensorimotor trajectories context and failure feedback and as context, but this is like on language model domain. So some on robotics domain is not working yet. So there are some projects still going on, but I think like the current models are not capable enough to understand trajectories as context. But hopefully in the future, like this direction can also shine more with more powerful models released for the field. Yeah.